So you cheated the system is what I mean.
No, it's only use one over.
It's not just what.
Yeah, you're like, I'm only gonna use this if you don't. It's not realizing I made a mistake.
I actually use whiteboards. Is that okay with you guys?
No.
Okay, everyone, you can use your clicker to check attendance. I'm glad we still have good attendance for the last class. I know some other graduate classes, half of the students are gone in the later part of the semester. Yeah, so hopefully you're all enjoying the class so far. Today is our last class. So we're going to finish the Toric code, and then I'll try to say something, about my perspective on quantum technologies at the end. Hopefully that's going to give you a kind of like a good summary of what we have went through so far. Okay, so first a couple announcements. So all your homeworks have been graded so far, so homework 1 to homework 5. If you find any grading errors, please let me know or let the TA know. I'm trying to be generous on the grading of the homework as long as you did a good amount of effort in finishing the homework. You should get some credits for it as long as you're doing the homework. I think the homework is really just helping you understand what we covered here. And the other thing is the final exam. If you have any sort of clarification questions, make sure you ask me either over the email or come to my office hours this afternoon. So that's my last office hour, and I don't have office hours next week. And the homework, the final exam is due next Wednesday. That's a hard deadline. It's just like a big assignment. Okay, and then I'm going to post the final grade probably a few days after the final exam. I also assign your bonus participation grade. I think I know most of your faces. I should be able to assign that grade. It's usually not negotiable. It's really dependent on if you're asking a lot of questions, answering questions, you'll get bonus grades for that. Okay, so for the Toric code, maybe I went a bit too fast in the last lecture, so I'll try to sort of review some of the stuff we said. So this is the lattice structure. So this is from the different sources. You can see I'm using the square to denote the qubit instead of the circle, but it means the same thing. So you kind of have a square lattice, but you actually put qubits, which are denoted by these little squares, on basically the edges of the square lattice. So that actually ends up with 2 times L squared qubits. If L is basically how many squares you have per direction, so that's 2L squared. In this case, we have 1, 2, 3, 4. So it's a 4 by 4 square lattice. So that would means you have 16 plaquettes here, but there's going to be 32 qubits because there are qubits defined on both the even row and the odd rows. And then we have 2 types of operators in the Hamiltonian. So we said that the Hamiltonian is made of the sum over the stars with the term AS and the sum of plaquette with BP. And we have a minus sign in front of everything, which is to make sure that the ground state is obtained by setting all the AS and BP equals to 1. So the ground state is obtained by setting all the AS and BP equals to 1. And we call that a stabilizer state. And the AS operators are basically made by the product of the sigma x operators belonging to that star. So basically, your product of these 4 sigma x and the BP operators is a product of all the, oops. That's weird. Let's try this again. Okay, there we go. The BP operators is a product of sigma z belonging to the plaquette P. Right. So you have 4 sigma z's in a product for each BP term. And then you basically go through all the stars, which are basically all the vertices here. So you have, basically 16 of them. You also go for all the plaquettes here. So apparently you have 16 of them in this 4 by 4 square lattice. So that's your Hamiltonian. And we said that because these AS and BPs, they mutually commute, and they're made of product of Pauli operators. So that actually form a stabilizer group, right? So that's a concept we mentioned in the last lecture. So all the commuting Pauli operators for n qubit, there should be 2 to the n of them. That forms the stabilizer group. But more interestingly, these AS and BP, they're almost independent of each other. So if you actually have n qubit, you can always find n independent stabilizers that generate the entire group. So independent basically means any one of the element cannot be written as a product of the others. So this is not exactly independent because we have this constraint that if you take the product of all the AS, so basically take all the stars and multiply the AS together, that actually goes to identity because of the periodic boundary condition. If you make all the product, each qubit is exactly covered by 2 sigma x, which goes to identity. And because of this, any given AS is basically the product, so let's call this AS prime, is given by all the product of all S not equal to S prime AS. And the reason why this, so basically means if you take any one of the star operator, it's actually equal to a product of all the other star operators. And so this is what I write here. So if you take a particular S prime, it's a product of all the other S of the AS operators. And so this actually directly follows from the previous equation because you can just multiply both sides by AS prime. So if you do AS prime, and then the right-hand side, you now have the full product. Right, because I'm multiplying AS prime to the right-hand side. And AS is a product of Pauli operator. So when you square it, when you multiply it with itself, it just goes to identity. I forgot to mention this, so now this should be more clear. So this is the reason why they're not independent. If the product then goes to identity, it means any one of them is really just a product of the others. So even though you have basically, so here we actually have n, stabilizers. So we have n qubits and we have n stabilizers, right? So half of it is in the AS, half of it is in the BP. They're not quite independent. So that means if you just set all of the eigenvalues to 1, it doesn't uniquely define a ground state because of this, dependency. And similarly, the product of all the BPs is also equal to identity. Because they're not independent, you actually don't get a unique ground state. And these two constraints actually will give you a fourfold degenerate ground state. And that is very important because this fourfold is actually because we are on a torus. We have periodic boundary conditions in both directions. So it's a topological invariant. And we can actually find the missing generator. So because we have n qubits and these stabilizers are not independent, so we actually only have n-2 generators. So the missing 2 generators, we can actually find them explicitly. It's basically that you have 2 qubits, right? You have 2 qubits degree of freedom. You have fourfold degeneracy. So for 2 qubits, there should be 2 generators, right? For n qubits, you should always have n generators for the stabilizer group. So those missing 2 generators are actually given by those loop operators we said at the end of the last class, right? So we have these loop operators in the z, in the horizontal direction and the vertical direction. And you can just choose these two as the missing 2 generators. So if you add these two together with all the AS and BPs, you make exactly n generators, and those will uniquely determine your ground state. So if you actually set, for example, the eigenvalue of this Pauli operator, this stabilizer to be 1, and that to be 1, it's going to give you, one of the ground state. And you can also set these two to be -1, right? So it's going to make 4 different combinations depending on the eigenvalues of these 2 generators. In principle, you can also choose the other 2. So you can choose a 2x as well. You can't choose a z and an x because these 2 actually do not commute, right? They always overlap at one particular point. And we know the sigma x and sigma z anti-commute. And for the generators, they have to be commuting, right? Because they're forming a stabilizer group. We only care about the commuting stabilizers. So you can choose either these 2 to fill the rest missing 2 generators, or you can choose these 2. So that's going to fully determine your ground state. The only thing that's important is these 2 loop operators, they can take either 1 or -1, but the other stabilizers have to take value 1. And the reason is just because they determine your energy, right? Because these AS and BPs all have to be 1, right? But the other ones actually, the loop operators can be either 1 or -1. So that gives you those 4 ground states. And we also said that these are very good logical qubit because in order to take one ground state to the other, you have to apply these loop operators in order to get from one state to the other. Any local operator is not going to get it. Okay, so that's what we covered in the last lecture. And I think I briefly mentioned about this code distance, which is, so this is actually a quantum error correction code. And the code distance is actually given by the linear system size L here. So here L is equal to 4. This is 4 by 4. Because you have to basically have a 4-body operator in order to make a loop, right? So if you want to loop around in any direction, you have to make that. So this is what the code distance means. You have to have an L-body operator to actually change the logical value of your qubit. The value of your logical qubit, and this L here is representing the code distance of the quantum error correction code. So any local errors that involves less than L-body operators will not change your logical qubit, the value of your logical qubit. So it's a pretty good error correction code. Okay, so the other thing I want to mention is about the excited state of this toric code. So we just talked about there are 4 degenerate ground state. And it doesn't mean that you can't destroy, you can't get outside of the ground state. If you have enough energy perturbation into your system, you can always get out of the ground state and get to an excited state. And that's of course going to destroy the information you stored in the ground state because you are no longer in the ground state. And we can calculate how much energy it requires to get out of the ground state. For example, if you are just looking at the Hamiltonian, the ground state has all these values to be 1, and the excited state, you would just imagine that maybe one of them has to go to -1, right, in order to go to the next lowest energy state. And it turns out that you can't just make one of them -1. You have to at least make 2 of them -1, and it's actually not so hard to see it. For example, if you just look at this picture here, let me use a different color. Maybe I have a plot down below. So yeah, I have one here. So you have to at least flip 2 of them. So here's an example. So suppose you start in the ground state, you apply a local sigma z operator on this particular qubit. So what it does is this star operator and this star operator will both take value of -1 instead of +1. +1 is in the ground state, but once you apply a sigma z, because sigma z anti-commute with this, it actually makes the star operator goes to -1. So let me show you why this is the case. So in the ground state, so let's just say this is a particular S here. So let's just say this is my AS1. On that, applying on the ground state, let's just call it precise 0, is going to be just equal to precise 0, right? So this is, because the ground state, all the stabilizers, all the AS and BP terms have eigenvalue 1. It's a co-eigenstate of all the AS and BP with eigenvalue 1. And then let's try to apply the sigma z to it. So let's say the z acting on the precise 0, I call that precise 1. It's some excited state. I just denote that by precise 1. And then we can try to see what is the expectation value of AS1 acting on the state precise 1, right? So let's just do a little bit of math here. So I get AS1 and z, and then precise 0, right? Just using this definition of what precise 1 is. And then because the operator z anti-commute with the AS, because AS is 4 sigma x here, right? So you get 4 sigma x, and this is a z operator, it anti-commute with that particular site. All the other side, the z does not apply on them, so it's fine. So that means anti-commute means I can swap these two, but with a negative sign in front of it, right? So I can do that. Okay, so now I have this. So this is AS1 acting on precise because it's a ground state. It's an eigenstate with eigenvalue 1, so that just becomes 1. So it becomes negative of S, a z acting on precise 0. So this just becomes precise 0. And then, according to this definition, it's just negative of precise 1, right, using this definition. So this means the AS1 applied on the precise 1 gives you negative of precise 1. So the precise 1 is still an eigenstate of these star operators, but the eigenvalue becomes -1 instead of +1. And similarly, you can show this star, I can call it S2. This other star here, this is my S1 and S2, will also get a -1 because the sigma z here, anti-commute with that sigma x. But all the other stars are actually still going to have eigenvalue 1. Because if I have a star over here, right, it's not even overlapping with z, then of course it's not touched, right? So all these other AS and BPs will also not change because this is a z operator that can commute with the plaquette operator. BPs get the product of sigma z. So it's not going to be changed by z. So you can do the same calculation. What you're going to find is that only in these 2 star operators, the eigenvalue change from 1 to -1. All the other ones, the BP or the AS, will remain the ground state value, which is +1, right? So now if you look at how we calculate the energy here, so what it really means is that, you know, instead of all of them being 1, 2 of them get to -1, right? So that means the energy increase is actually going to be 4, right? Because there are previously 2 of them are 1, now 2 of them are -1, so the energy difference is actually 4. So that's actually the energy gap between the ground state and the first excited state. So you know, adding a single sigma z, that's the minimum energy you can, you know, excite to the system. You can never just flip one of the stars, just because, you know, if you apply any local party operator, it's always going to change at least 2 neighboring ones. And similarly, if you apply a sigma x, you're actually going to flip 2 plaquettes. I didn't show it, but the idea is very similar. For example, if you apply a sigma z here, let me use a different color, then you're actually going to basically flip this plaquette, because the if you apply a sigma x. So you apply a sigma x operator here, it's going to flip this plaquette and this plaquette. So these 2 plaquette operators, these 2 BPs will get -1 instead of +1. All the other ones will be untouched. So you're always going to flip 2 of them. So the energy gap is actually 4, which is good. So that means, as you know, so there's some coupling strengths I didn't talk about in the Hamiltonian. You can always put some J here as the energy unit. So as long as you don't put energy that is larger or equal than 4 times J, you're going to be mostly staying in the ground state. So you're basically protected. But of course, these topological sort of qubits, they're still not robust under like a sort of a high energy perturbation or like a high temperature excitation. If you really heat up the system, if you put a lot of energy into the system, of course you are going to destroy the information encoded in the ground state because you are going to be excited higher up. So the key thing is, in order to have this protected qubit, first you have to have local perturbations. You can't have a perturbation that looks like a loop operator. And the second is, the amount of perturbation, the energy of the perturbation has to be smaller than the energy gap. The smaller the better, right? Because we know quantum mechanically, even though if the energy is smaller, you can still get a little bit of excitation into the excited state, right? Because it's just governed by probability. Classically, if you don't have enough energy, you're never going to be excited. But quantum mechanically, you can still get excited a little bit. So you want the energy of the excitation also to be low. So those are the 2 requirements to protect your qubits if you encode your information in the ground state of the toric code Hamiltonian. So if you can actually find, if you can actually simulate this toric code Hamiltonian, or if you find a material whose Hamiltonian is just given by this, that would be great, because we can use that to at least store our quantum information there for a really, really long time. But unfortunately, we don't have any ways to simulate this Hamiltonian directly. So first, there's no native material that have this weird type of interaction. It also has to be on a torus. So that would be very hard to find a material that's shaped into a torus. And the other thing is, even if you're using, say, a quantum simulation approach, it's very hard to simulate these 4-body interactions. So there are some toy experiments about doing this with just 6 qubit or 8 qubit, but I don't think it's scalable. So that's kind of the catch. If you can really make this Hamiltonian, what you basically get is something called a self-error correcting code. I talked about this briefly. It's also called passive error correction. So basically, as long as you have this Hamiltonian physically, and you cool the system to the ground state, you're good to go. You don't need to do any other things. The information is just encoded in the ground state, and it's going to be there for a very, very long time. The lifetime will depend exponentially on the system size. So you can basically make the time almost indefinite. So since we don't have that, there's another approach to do this, which is basically something called active quantum error correction code. So I'm going to briefly talk about this in today's lecture. Some of you might have already learned concept related to this in your Physics 519, the quantum information class. If you have the Hamiltonian, it's called self-error correcting system. But if you don't have it, this Hamiltonian, this whole idea of the toric code is still very useful, because it actually belongs to the best quantum error correction code we have discovered. So what does an active quantum error correction code mean? So suppose we can't realize this toric code Hamiltonian. What we can do is the following. So we just need a 2D array of qubits prepared in the ground state of the toric code Hamiltonian. So what you need to do is just to prepare the ground state of the toric code Hamiltonian. So that's a much simpler problem. I don't need to engineer this Hamiltonian. I just need to prepare a state that looks exactly as the ground state of the toric code Hamiltonian. It's not easy, but you can always find a quantum circuit that can prepare the state, right? Because in principle, you can diagonalize this Hamiltonian numerically to find what the ground state look like. You just need to find a quantum circuit that creates the exact ground state on your quantum computer. It's not easy, and we said in the previous lecture, in order to create this state, you will need a quantum circuit whose steps is at least proportional to the system size, right? Because if you're going from the product state to the ground state of this, you are preparing intrinsic topological order state, which is long-range entangled. So you can't do it very easily. You have to have a long circuit to do it. But that's fine, right? Because a circuit depth of n, of course, is not very good, but you can still do it. So that's the first step. You prepare the ground state. So once you prepare the ground state, you can do quantum computing with it. Of course, in this process, you might actually get errors, right, on your logical qubit. So you have you can encode information into one of the 4 ground state of this toric code, right? Because you have 4 degenerate ground state. In principle, you can encode 2 logical qubits into that ground state manifold. Of course, because you don't have the Hamiltonian, we don't have the energy gap, you can have errors, right, in this computational process. But the cool thing is you can actually detect these errors in a very good way. So let's just say if we have an error in the system, so what's going to look like? So if you know a little bit of quantum error correction, most of the errors on your qubit can be represented by either the bit flip error or the phase flip error. So I'm just going to write it here. So you can have either a bit flip error, which basically means the qubit goes from 0 to 1 or from 1 to 0. So you flip the qubit, so that's a very common type of error, especially in classical computer. That's basically the only type of error you can possibly have, right? The information should be encoded in 0, but then it goes to 1 for whatever reason. And there's another type of error which is unique to quantum, to qubits. It's called the phase flip error. So what that means is that suppose you have a superposition of 0 plus 1. It actually goes to 0 minus 1. Right? So basically the phase gets an error. So the plus sign becomes a negative sign. And these two can both be modeled directly by Pauli operators. So this is basically just the x operator, because if you apply the x operator on 0, it becomes 1, right? Because sigma x just flips the qubit. And this is actually, the error is denoted by the z operator. So if you apply the sigma z on the 0 plus 1, it becomes the 0 minus 1, right? So it's basically the x error and the z error. So you might wonder, what about other errors? Because we have a superposition state, right? It could be any, it could go to any other state, if it's some error comes in. So it turns out any other error can be made as a superposition or a combination of these two, right? For example, you might wonder a y error. So if you apply the y on the state 0 plus 1, right? So that actually goes to, something like a 0, like minus I1, I0 minus I1, something like this, right? So that could also be a potential error. But the thing is, we know that the y is just made of x and z, right? So y is actually equal to I times x and z. I might get a wrong sign there. But the sigma y, you can really write it as a product of sigma x and sigma z. So that means if you have any other kind of errors, you can always write it as some combinations of bit flip and phase flip, right? Because x times z equals to y. And if you have both x, y, and z, then you can pretty much make any operator, right? Because it's a complete basis for a single qubit. So that means we pretty much just need to understand how we can correct the bit flip error and the phase flip error, right? So quantum error correction code is basically designed to do this. So you want to know that which qubit undergoes either a phase flip or a bit flip error, and then you try to correct it by undoing the error. And correcting the error is simple. If you actually know, for example, your third qubit has a bit flip error, you just apply another sigma x to it. Right? So once you know where the error is and what type of error it is, you can easily correct it. So then the main question for quantum error correction is, how do you detect the error, right? So this is something called error syndrome measurement. And in terms of the toric code, you can actually measure the error pretty easily. So I kind of just said, right? So for example, if this qubit has a phase flip error, you have a sigma z operator that applies on the qubit, you can just measure all your star operators, and then you will find that these two star operators will actually now becomes minus 1 instead of plus 1. So that's kind of your syndrome, right? So you basically measure all your AS and BP operators. These are not so hard to measure, right? Because each operator is just made of a product of sigma x or sigma z. So you just need to measure all your qubit in the sigma x direction, and then you can basically calculate all the AS operators value. So you don't actually need to do exponential many measurements. You basically just measure all the qubit in X, and then you can calculate each AS operator independently. So that's not very hard. And similarly, you can measure all the the BP operators by measuring the qubit in the Z. So then you basically know which one. So in this case, you will know this qubit has got a z there. And for example, you have two qubits which both are having phase flips. You have two sigma z's. Then you are going to find that these two will have if you measure that, it will get +1, -1 instead of +1. All the other ones should still be in +1, right? Because you're starting the ground state. And the reason why this middle one actually is not flipped is because this middle star here, actually you get two sigma z's, and that actually commute, right? So for the same calculation, if you get two sigma z's, this particular AS will still have eigenvalue 1. So it will still be measured in 1 instead of -1. So you won't have any syndrome here. So you only have the syndrome at the edges. So that's kind of the interesting thing about it. And you can look at sort of more complicated errors. So for example, if you have a sigma z, a string of sigma z, that's you have a lot of qubits that are undergoing the phase flip. This is usually unlikely, but in this case, you'll find only the two star operators at the edges will return a -1, and all the other ones are still going to be +1. And similarly, you could have in this case, you have two z errors here and two z errors there and one z error there. And if you measure it, you will find that all the blue crosses will give you -1 instead of +1. So basically, by measuring all these AS and BPs, you will actually be able to locate where the phase flip or the bit flip errors are, right? And here I'm only looking at the stars, but if you have the bit flip errors given by sigma x, you need to measure the plaquette operator. So the plaquette will be flipped, right? I kind of show you this idea, right? If you have this, this middle qubit, so this one's got a bit flip error given by x, then those two plaquettes highlighted in green, if you measure them, they will be -1 instead of +1. So this is called the error syndrome measurement. So in the toric code, you can actually detect these errors very easily. And of course, once you detect the errors, you can just correct them by applying this operator again, right? As I said, right? If you know where your error is, you just apply that operator. It's just a single qubit rotation, just a single qubit gate. So you can apply it to fix the error. So this is how we do error correction. Okay, but if it's just like this, it would be too good to be true. So there's one catch to it, which is the reason why. If it's really like this, you can pretty much correct any error. So there's even no threshold, right? So even if you have half of the qubit wrong, you can still do it, right? Because as I said, you can actually correct multi-qubit errors, right? You can always locate where the error is. But there's a problem, and it's kind of related to the multi-qubit error. So let's look at the error in this way. You have 5 sigma z, 5 phase flip errors in this way. And that will denote that these two star operators will basically return the wrong value. They will give you -1 instead of +1. All the other AS and BPs, they will still give you the same measurement as in the ground state. Okay, so you would think that I can just correct the errors by applying the sigma z in these 4 qubits. I should be able to revert the error, right? But there's a problem. So there's actually a different type of possibility that you get 2 of these blue star operators flipped. You could also have an error that goes like this. So there's like a sigma z, and then it wraps around the torus, and it goes up, right? So if you look at here, what you are going to find is still only at the end of the stream you will have those 2, star operators flipped, because only at the end you will get it, right? In the middle ones, the stars always get 2 sigma z's, so they are not going to be flipped, right? So it's only the ones at the end that will get you the wrong value. So this one seems to have exactly the same error syndrome as this. So that's a problem. There could be multiple different types of errors that gives you exactly the same error syndrome. And how many different ones? There's going to be 4 of them, right? So this is another case, like you wrap around this torus in this way, in the horizontal way, and goes here. And this is like you wrap around in both directions. So this goes here, and this goes here to the right. So you can actually wrap around the torus in different ways, and that's going to create exactly the same error syndrome. Question?
Couldn't you have other orientations of those strings that don't even wrap around the torus if you just stay on the same?
That's a good question, but they are topologically equivalent. So for example, you can sorry. So this one you don't need to connect the z all the way from here to here. You can, for example, go a little bit of detour. But as long as they don't wrap around the torus, the topological equivalent means that, which basically means that they will give you the same state. Because you're applying on the ground state. So let me actually show you. This is a really good question, right? So you're basically asking, what if I actually, for example, add a z here, right? So I go a detour here, right? So that's a very good question. So this, if you do this, it's actually going to give you the same state as this current plot because you're basically just adding a blockade operator here. So those two only differ by applying a blockade operator. And a blockade operator, the ground state and the excited state, they're both eigenstate of it. So when you apply that extra blockade operator, it's not going to change the state at all. So their topological equivalent means that if you just detour this, it's going to make you the same state. It doesn't really matter. So it's not going to create a different state. What is different is if you actually loop around, that's going to create a different state because we know the loop operator can actually change your logical qubit. So if you don't know which topology your error actually corresponds to, you can actually end up correcting the error in the wrong way. So for example, the real error is actually in this topology. They don't actually loop around the torus, but you use this one, you're actually going to flip your logical qubit value, which is really bad because you actually make an error by doing error correction. Question?
Yeah, so like about how many physical qubits do you need to
Uh-huh.
make one like decent logical
Yeah.
qubit with this? Because this is n equals 4 and that doesn't look great for
It doesn't. Yeah, it really depends on how much error you want to get protected. As I said, the code, the error, especially because most of the errors are local errors. Then if you want to get like a global error, it's basically like an exponential problem, right? Suppose each qubit has 10% of getting flipped. If you want to get a loop operator, which means all your 4 qubit has to be wrong, right? The error has to simultaneously apply on all 4. Then it's 0.1 to the 4th power, right? So it becomes 10 to the minus 4. Right? But if you have like L equals to 10, then that error rate becomes 10 to the minus 10, right? So you're right. This L, 4 is not very good, but you can easily just make L equals to 10 and you get 10 to the minus 10 error. Because it's that exponential scaling, you can make this error very, very small quickly. Yeah.
And then in that case, that upper left error is also a lot more likely if that's the error. Right?
Yeah, probably, yeah. Yeah, especially we have such a small system and having like, 4 sigma z's, that's not too small, right? It's 10 to the minus 4 if your error rate is 10%.
Whereas the other
Yeah.
ones are...
The other ones are probably less likely, right?
The bigger
Yeah.
you make the system, the
Yeah.
more likely it is that
Yeah,
it's that one.
but you have to worry about it because if you correct it in the wrong way, you will get an error, right? So in mathematical terms, these are actually called homotopies. So these are 4 different homotopies of the error syndrome. And the problem is you have to know which error it is, right? So you can't, if you get the different topology, then you're making an error. So to do that, that will take probably 2 more lectures. So I'm just going to briefly, talk about this. So it's a non-trivial task to choose appropriate correction operator. You have to know which of the errors it belongs to. So there's a dedicated thing that does this. It's called decoders. So for most of these 2D error correction code, we're going to later talk about it. It belongs to a big class of error correction code called surface code. You always need a decoder. And the decoder is going to make sure that you're using the correct topology. You're recognizing the correct topology for the errors. So the decoder is something that is sort of a pain here. And the decoder, will only work if the errors is below a certain threshold. So if you have every qubit being 50% possibly wrong, then the decoder is not going to work. So of course, in that case, it's kind of like what Aaron just said, right? So it has to assume that, for example, this error is less likely than that. But if you get 50%, then maybe you can't really determine which one is the correct one. But you can roughly say that if the error rate is small enough, then this one is likely going to be much more, it's going to be much more likely to be the actual physical error, right? So you have to know something about the error rate, right? If the qubit are very likely to be wrong, then you can't really know which one it is, the correct one. So for the toric code, the optimal decoder gives you a threshold which is 11%. I'm not going to talk about how we get it. So this is coming from some very complicated theoretical calculations. So you get 11% threshold, which is pretty high, right? So because right now most of our 2-qubit single qubit gates can be done within 1% error, and sometimes within 0.1%. We get 3 nines. That's kind of the current record. So 11% is pretty generous, but there's a problem here. So this is what's called the optimal decoder. So this decoder is like doing the best thing. If you have the best decoding algorithm, you can tolerate 11% of physical qubits error. But of course, the problem with the optimal decoder is not efficient. So you have to take exponentially long runtime on a classical computer to figure out which of the 4 topology should be your error. So that's of course not good, right? Especially if you have a large number of qubits. And the good thing is you can use something that is not optimal. So it's kind of like some efficient decoding algorithm, which is not necessarily optimal. And one of the commonly used ones is called the minimum weight perfect match. So you can search this on Google if you want to know more details on how people use this. So this is actually from graph theory, because this is kind of like a graph problem. You can use some more efficient algorithms that only scales polynomially with your system size. So they're not going to give you the best error threshold. In this case, you can see the error threshold is a lot lower. So with this more efficient decoding algorithm, they can only tolerate about 0.75% of error, which is still pretty high, because right now we can do gates with basically less than this error. So that's kind of the idea. But there are even better sort of versions of this. This Tori code is kind of like the first discovered surface code, and there are other two-dimensional error correction code. I think the best one can actually have error rate which is a little bit better than this. It's basically 1 or 2%. So it's about at least it's basically a couple percent. So that's the best threshold for efficient decoding algorithm. So this is still way better than the typical error correction code. So if you don't do these topological error correction code, like just do, for example, the Shor's code, which is like a non-topological error correction code, usually the error threshold is like 10 to the minus 5. And we can't actually get to that low error threshold for our current physical qubit. Usually we're on the 10 to the minus 2, 10 to the minus 3. So that's our current error threshold. So that means these surface code, or even the Tori code, can already be satisfied. So the error, you can already satisfy this error threshold. So in principle, you can really do this. You can get topologically protected logical qubit. But of course, there's a big catch. That is, you need to have a lot of qubits, right? So you need to have 2 L square qubit, right? L is the system size, and how large L it is depends on how low you want to push the error. So typically the L you want to push is going to be about 100 to 1,000. So it's actually not as good as I said. It's just like 10 to the minus L. It's actually worse than that. So that means if you want to get like a really good fault tolerant qubit, meaning the error rate is going to like 10 to the minus 15, or 10 to at least less than 10 to the minus 10, like a classical qubit, then you will need about at least 10,000 qubits. So basically L has to be about 100 in order to make this working. But suppose you can really make this many qubit, you can make 10,000 qubit and have an error threshold of less than 1%, then you can really make one logical qubit that is as good as a classical bit with 10 to the minus 15 error rate. So I think Ada used to say that we just don't appreciate how good classical computers are until we are making quantum computers, right? They're just extremely good. Of course, the big catch is a classical computer that can encode superpositions, right? So there's a fundamental difference between the two. Of course, there's a long way to go, but there's a possibility here, right? So if you do have that many qubit, even just making the error rate about 1%, you can make a logical qubit, which is basically flawless, right? So that's still a very big advantage. And personally, I really think this is probably going to be the way towards fault-tolerant quantum computing. So there are multiple ways to do it. Of course, you can make this self-error correcting code. In that case, it would be great because you don't need to do all these gates, right? If you can engineer that Hamiltonian, then that's it. You don't need to detect all these error syndrome. You don't need all these. It's automatically corrected. But that's probably very hard. And Microsoft is looking into that, right? We talk about that. They're interested in making these Majorana fermions, which is kind of like that self-correcting error correction code. And the other way is you just make a lot of qubits, right? Right now, we can already make about 100 qubit with this error rate. If you can scale that up to 10,000, then you can at least make one flawless qubit, right? So it seems like it's more like an engineering problem, right? If you can make 100, maybe you can make 1,000,000. Of course, there's going to be significant challenges there. But at least this seems to be the way to go. Okay, so that's for the active error correction. So you don't need to simulate the Hamiltonian. You just need to engineer the ground state, prepare the ground state, do error detections, and then apply these error corrections. Of course, we need this decoding algorithm, which will require the physical errors to be sufficiently low, but not too low. Okay, so the last thing I want to talk about is anyons. I promise you that I will explain to you how the anyons actually work in 2D and why we can get anyons in 2D. And the Tori code is probably the best textbook example. And we can actually just look at this picture here. So maybe we can look at the picture here. So what does the anion mean here? So suppose we just have that sigma z there, and then we're going to create 2 stars, right? So we can view these 2 stars as errors if you're thinking about error correction. But if you're just thinking about a condensed matter or many-body physics perspective, so the ground state is like all your AS and BPs are in 1, they're perfect, there's no defect there. And the first excited state, you will get 2 of these stars, to be flipped, right? So you can actually treat these two stars as like quasi-particles, because you can, for example, in this case, if you apply 2 sigma z's, these two quasi-particles still exist, but they are like further apart, right? So you can really treat that these two blue crosses, they are errors, but you can, in this case, you can actually treat them as particles. So whenever you excite the state, so both of these are first excited state, because you have 2 of the AS flipped, right? The energy difference to the ground state is 4, as we just said. So these are first excited state, and they're actually made of 2 quasi-particles. And in this case, Kitaev called these, these star operators flipped to be the electric charges. He said that is kind of similar to electric charges, but for whatever reason, you can just call these some quasi-particles. He called them electric charges. So the first excited state will contain 2 electric charges as a quasi-particle, and you can actually move them around. So that's kind of the cool thing. You can see that by applying another sigma z operator, I can basically separate these 2 anyons, and you can apply the sigma z, for example, in this case, right? You can apply more of them to move this. For example, the first, neighboring like the top one. You can apply sigma z's to push this anion all the way to the bottom. So you can keep doing this, and if you do this, well enough, you can actually move one of them around the other for a whole loop, right? So that's kind of the braiding we talk about. By applying these sigma z's, you can actually move one around the other. And you don't actually have to go around the torus, because if they're close, you can really just, move this, like this, right? You don't need to loop around the torus. You can just do this. So this means you can actually braid these 2 anyons and possibly get, a non-trivial phase, right? So in this case, if you're just dealing with 2 electric charges, if you move them around, you're not going to get anything, so you're just going to get the same wave function. So that just behaves like bosons. If you just move one across the other, it's actually not too hard to prove. I add some proof at the end of the lecture notes, because you're just using a bunch of sigma z's that all commute with each other. If you move around one circle, you're just going to get back to your original function, wave function, which is not that interesting. And similarly, you can deal with the plaquette operators. So for example, if you apply a sigma x here, you're going to flip 2 plaquettes. You can also think about these 2 plaquettes as 2 quasi-particles, and Kitaev called them magnetic charges. You can apply 2 sigma x to separate. So if you apply 2 sigma x, let me actually erase this to show you what's going on. So if you apply 2 sigma x operator, you end up with 2 plaquettes. So the middle one is actually not flipped because you have 2 sigma x, so it's still in the ground state, so we don't show it. We only show the flipped plaquette. So if you apply these 2 sigma x, you're going to basically make these 2 plaquettes separated, and you can apply another sigma x to push this even down further. And in principle, you can push one around the others by a whole loop. And if you show that, this is also just going to give you the same wave function. So that seems like these are not really interesting. They're just like bosons. But then something weird is happening. If you try to push a star operator around a plaquette, so you treat the star as a quasi-particle and the plaquette as a quasi-particle. If you do one around the other, you actually get a negative sign. And the reason is actually because of the sigma x operator do not commute with the sigma z operator. It's something related to that. If you want to see the mass, I basically showed you some mass here. So these precise E's, so those are the excited state with a pair of electric charge. But if you're moving an electric charge around a magnetic charge, you will actually get a negative sign. And the reason is kind of related to the fact that the operators z and x do not commute. So you actually get an exotic, mutual statistics. Because if you think about all the electric charges as bosons, all the magnetic charges as bosons, then you end up with a problem. Because if you move a boson around the other, you should always get the same wave function. But in this case, it's not. If you move one type of boson around the other type of boson, you actually get a negative sign. So the only way for this to happen is these are actually not bosons. They are actually anyons. So these do not belong to bosons. So it's a mutual statistics of these 2 type of particles that gives you a non-trivial statistics. It gives you a minus sign. And you also can't think about them as fermions, right? If you move one fermion around the other, yes, you will get a minus sign. But if you move the same type, it don't give you the minus sign. So it's kind of like a strange particle. It's neither a boson nor a fermion. So this is why Kitaev called them anion. In this case, it's a Billinger anion, because what you get is just a minus sign. So you can't really use this for quantum computing. So the toric code is not, you can't directly do topological quantum gates using the toric code. You can use it as a quantum error correction code or use it as a quantum memory. But you can't directly do quantum computing just because they are abelian anyons. So those excited states don't give you any quantum gate. So if you want to do topological quantum gates, you will need to use a more complicated model. It's called the Kitaev honeycomb model. So it's actually defined on a honeycomb lattice. It's also exactly solvable. but it's much more complicated than the toric model. If you're interested, you can read that paper. It's also pretty important. So this one, the elementary excitations are actually given by Majorana fermions. So when you move one across the other, around the other, you will actually get a non-trivial quantum gate. So that's the thing. You can't do topological quantum gate, but at least you can do error correction in a very efficient way, or you can store the information there. So that's basically the use of the toric code. It's still very useful, but there are other generalizations of this. Okay, so that's for the toric code. Any questions? Yeah.
For the error syndrome, will decoders always be needed, or is there some work to be done, like where you can change the physical structure to kind of reduce redundancy?
I don't think so, because there's something, if you, for example, you don't need the decoders if you have open boundary condition, right? Because then you can never loop around things, right? But the problem is you will immediately lose your topologically protected ground state. Right? So there's something that always, there's always a price you have to pay. The reason why these informations are local to, sort of robust to local perturbations is because you have this topology, and it has to be defined on the torus. And because it's defined on the torus, then you have these different type of errors that are, have different topology, and then you have a problem there. So they always go one by one. Yeah.
If you have an error syndrome that has 3 or more of these excited quasiparticles, do you still have the topology with kind of 4 ways to create those combinations of 3? Or
So you can always, because
that's more complex.
So if you have, for example, more than 2 of this, you're saying they always have to be in pairs, so you can have 2 of them here, maybe 2 of them there. Yes.
Okay.
Yeah, you still have this problem, and usually you just correct one pair of error first, and then you correct the other ones. You can treat them independently.
Okay.
Yeah. Okay. So I have a bit of time left. So I want to first show you a quantum simulation experiment, and then we're going to talk about something more general from there. So I'm not going to finish the entire slide stack here. This should be because we have some classes missed this semester. But if you're interested, you can you can just look over this slide yourself. I will upload it to Canvas. So this is kind of talking about different platforms for doing quantum simulation. They're also related for quantum computing. So I listed 3 pictures. There's a code add-in on the left. The middle is ion trap, and the right one is basically a superconducting qubit system. And I don't want to talk too much about the introduction. I think most of you are already familiar with this. I talked about this in the first class. So the reason why we're doing quantum simulation, and we can basically simulate different quantum matter, and that can be upgraded to a universal quantum computer. So I do think that the quantum simulation is currently the most important application of quantum computers, because we're not very close to a fault-tolerant quantum computer. There's very limited things we can do. But quantum simulation is fine, because we can actually already simulate these interesting interacting quantum particles, about 100 or even more, and that's already hard to model classically. So we can possibly discover some new physics or some new chemistry. So that's kind of the main application of quantum computers right now. For example, I talked about this adiabatic quantum computer. You can simulate the Ising model and then try to minimize it. So this is also kind of marketed as a near-term application of quantum computing. It's quantum annealing. It's called quantum annealing. So you're trying to minimize this quadratic function here. So the question is whether this could maybe solve some large class of sort of optimization problem classically, for example, like a travel salesman problem. But the catch is that we don't actually know there's going to be a quantum speedup. So there's multiple reasons. The first is, even if you can sort of do this exactly, for example, you just have this perfect Ising model, and then you apply some transverse field to get to the ground state, then it's not very clear if there's always a quantum speedup, because the energy gap is going to basically close when you do this adiabatic process, and how much time you actually need to make sure the system is adiabatic. So that's actually not well known. I think even the best complexity theorists cannot really predict that this quantum annealing can actually give you a provable speed up over the best classical algorithms. So most people think that it is probable that you get a polynomial speed up, maybe a quadratic or cubic. or even higher, order of polynomial speed up. But it's unlikely that this is going to give you an exponential speed up. Yes, you can encode the travel salesman problem into this, and a lot of these really hard MP problems into this finding the ground state of the IC model. But most likely, there's only going to be a polynomial speed up when you are doing this on a quantum computer. So you're most likely not going to get exponential speed up. And the other problem is, in an actual experiment, you can't actually make an IC model perfect. You can't find the ground state because there's always going to be noise in the system that's going to heat up. At the end of the day, you're never going to get the ground state of this Hamiltonian. You're always going to get some sort of low temperature state. And whether that's going to even ruin your quantum speed up is also not clear. For example, there's this big Canadian company called D-Wave. They've been doing this quantum annealing for many years. And most of the remaining quantum computing community don't treat D-Wave very seriously because of the problem that, I can quote, this. So basically, Chris Moreau thinks that the D-Wave system is a joke. I think that's a little bit of mean. But in some sense, he's partially right because the D-Wave system, there's so much error in it that it's really not very quantum. It's more or less semi-classical. There's so much noise, so you're usually just getting some sort of finite temperature state. So you're never going to get even close to the ground state. Then this whole idea of quantum annealing is not really implemented by those D-Wave machines. So there's always problems to this. There's kind of like a better version of D-Wave. I think there's a company, it's a startup company by Harvard, it's called Cura. Some of you might have attended talks by their spokesman. And they can do things better than the D-Wave. They can control the error and the temperatures relatively well. But even in their case, they can't really guarantee that we're getting to the ground state. So whether we get a quantum speed up is also not clear. But they are also publishing a lot of things on what kind of industrial problem can be mapped to quantum optimization problems of this. So it's certainly interesting. But one of the news I heard, because I have some friends who is working at Cura, is they're also secretly switching to quantum gates. So they're not doing quantum annealing. And they told me that the industry is just not too much interested in quantum annealing. They're still interested in doing these universal quantum computers, like you actually do quantum gates, and you want to go fault tolerant in the future. That seems to be the mainstream. Most of the the industry is still looking at universal quantum computer and fault tolerant quantum gates. Okay, so here's kind of an interesting plot. If you think about all these different quantum hardware platforms, so we have trapped ions, superconductors, all the way to neutral atoms. There seems to be like always a trade-off in terms of the amount of control you can get and the number of particles. So the trapped ions and superconductors, you can have very good control, very high fidelity gates, but you don't have a lot of qubits. On the other hand, if you go to like these neutral atoms, you can easily trap like 1 million atoms in the optical lattice. I showed you this lab by Emmanuel Blob's group in Europe. So they already have like tens of millions of atoms there. They can also do some sort of individual control and imaging, but definitely they can't do high fidelity gates. And there's a limited amount of control you have. For example, it's not very easy to do like a 2-qubit gate there. Usually they can only control things globally. So they are very good for quantum simulation where you don't need this individual qubit control. But if you really need very good control and very high configurability, you will probably need to go for the platforms on the left. But then you are going to lose the particle number. There seems to be a dilemma. And I think it makes sense, at least from an engineering perspective. The more control you have, you can't really scale that up easily. Of course, at the end of the day, we want to go here, right? So kind of there's like a dash line where you can't do this on a classical computer. I think right now we can already get close to this, like these quantum supremacy experiment, they're kind of demonstration of that. You can probably get a little bit past this, but not generically, especially for interesting applications. So we're kind of at the edge of crossing that border, going into the real quantum world that there's no classical analog that can be used to predict. Okay, so I would say that at this moment, only these two hardware platforms are actually leading in terms of quantum computing. So one is trapped ion, the other one is superconducting qubit. So both have a lot of startups already. The superconducting qubit by far have the most number of companies. There's IBM, there's Google, right? There's Rigetti, there's Intel. So even Amazon invested in it. The trapped ions, they have IonQ, which is run by Chris Monroe. And then there's Amazon, Honeywell, which is also renamed to Quantinuum. So there's a local company here doing trapped ions. They already have like a few hundred people there. So all the other ones like neutral atoms, quantum dots, they're not even getting close to have say more than 10 qubits with good fidelity gates. So these two are the leading platforms for a number of good reasons, but there are also like pros and cons for these two different platforms. For example, for the ion traps, the good property is that they have really long coherence time. You can easily get longer than a second. But I also want to say that this coherence time is only achieved in the dark, right? If you don't perturb the qubit by lasers, they can store some superposition of 0 and 1 for at least a few seconds or sometimes even minutes. But if you actually shine lasers on it, it's going to actually make them decohere much faster. Usually you will get only about 10 or 100 milliseconds. So it's definitely going to be less than a second if you actually shine, if you're doing operations. If you don't do operations, you just want to store the information, that's very good. And you can already have about 50 to 100 qubits demonstrated. I still think IonQ's, the best quantum computer is only having about 20 qubits-ish. I recently had a collaboration with them. But that's kind of the scale there. But they can do very good quantum gates. So the gate fidelity is basically higher than 3 nines, 99.9, about 5 years ago. So they achieved that already a long time ago. The superconducting qubit got that also a couple years ago. All the other platforms can hardly do that. I don't think they can get 3 nines. So there are also challenges with the trapped ion systems. The first is you need lasers and optics, because you basically need lasers to flip these the qubit carried by the atoms, because atoms have optical transitions, and the gates are usually very slow. So usually the 2-qubit gates are on the order of milliseconds or maybe a few hundred microseconds. So they're not very fast, and you also need cryogenics. But you only need about 4K. So you don't need a dilution refrigerator. And of course, you need a lot of engineering. And one of the big advantages is that all the qubits are actually connected, so they're kind of having these long-range interactions, which is my favorite. And you can also reconnect these, reconfigure these connections. For superconducting qubit, it's kind of a little bit complementary. The coherence time is usually short. You can get to a few microseconds. That's usually the case. It's much shorter than the seconds level. But you can also do gates very fast. And the gates, I think the fastest one can already be like a few tenths of nanoseconds. So it's really fast, about 1,000 times faster every time scale. And you do need very good cryogenics. So it's about 10 to the minus 2 Kelvin. So you need a dilution refrigerator, which is, of course, very hard to engineer. But the good thing is you don't need the lasers. You just need to apply a bunch of voltages to do those quantum gates. It's a circuit, right? So you don't need lasers, you don't need optics, but you do need cryogenics. Otherwise, the qubit is going to decohere at high temperature. So you can also possibly scale these systems by using printable 2D circuit and all qubits. So one of the things is it's not really reconfigurable because everything is just wired. It's really connected by wires like a circuit. And the other thing is all qubits are different because these are solid state qubit. Each qubit can be a little bit different depending on the defects in the solid. So they're not identical, so which could be a pain because you need a lot of calibration effort to make sure you know what are the frequencies of each qubit. And for example, Google spent a lot of time calibrating their qubit, especially if you have more than 100 of them. It could be very, very painful to calibrate all the qubits. Usually they have some sort of automatic machine learning process to do that, and it still takes a long time. On the other hand, the trapped ion cases, all the qubits are made equal by the nature because these are atoms, right? The atoms are indistinguishable by quantum mechanics. So they're always the same. But of course, it's also harder because you have to trap them and you have to use lasers. So there's pros and cons. At this point, I don't really know which one is going to finally win. You don't know which one is going to be the ideal platform. We don't really have one that is clearly going to be the winner. And I'm quoting this sentence from Bill Phillips. Actually, he was actually at University of Maryland, so when I was a postdoc there, and he basically thinks that it is not good to just support one platform. It's always good to invest, in multiple platforms, just for diversity and also for the fact that maybe one of them is going to show up to be better than the others. We just don't know, right? So there's definitely also people pursuing other platforms for this reason. So we can't just put all eggs into one or two baskets. So that's for the hardware platform. And yeah, question, yeah.
So state of the art for superconducting, you got 50 to 100. IBM's latest announcement was...
Yeah, so this one is not I haven't updated this. I think IBM's got 400, but it's not, and the problem always is if you go to larger number of qubits, then you lose control and the fidelity is going to be worse. And there's other problems there. And just imagine that you need to have a lot of wires there. So the crosstalk and all kinds of troubles will probably creep in.
And that was the reason for my question. I wasn't sure if that's your perspective.
Yeah, I think, at least it's going to be a huge engineering challenge. At the end of the day, you can probably push both the number of qubits and the fidelity, but it's going to require a lot of engineering effort, right? That's for sure. My personal take is we're probably not going to see any sort of useful commercial profit out of these devices anytime soon, because I can give you like one number. There are people studying quantum chemistry, which is also believed to be one of the near-term applications. So there are some of these molecules you want to calculate the free energy, and they're very hard to calculate it on classical computers. It's definitely very important because, for example, if you want to find some new drugs, then you need quantum chemistry, right? So quantum chemistry is probably like a lower hanging fruit for quantum computing applications. And so the most optimistic estimate for doing something that's better than the best classical computer for quantum chemistry problem is that you need 40,000 gates. 40,000 gates. So that's the most optimistic. It's like the best application. There's like this molecule. You need to solve the Schrödinger's equation, and if you can do 40,000 gates with good fidelity, then you can actually